Greetings. Part 1 of Characteristics and Application series for induction machines consists of machine fundamentals. And this includes conversion of energy, steady state operation of machines, motor and generator actions, ratings and motor equations, including the speed equations, efficiency and power factor versus percent loading of the machine, motor feeder cables, sizing based on voltage drop and ampacity and other load flow solutions. So to start with conversion of energy, we're going from electrical to magnetic to mechanical energy. The first part on the electrical side, we deal with electromotive force, which is designated by capital letter E, and that is your EMF. The second part on the magnetic side, in a vertical condition, in phase with the F sub A. When we go to phase B, when phase B is maximum, the A and C currents are negative and equal half as much as phase B, and therefore the MMF would be in direction of phase B MMF. And you can see now that the total MMF of the system rotates from phase A to phase B and so on. It would rotate to phase A, B, C. And if I go through the process of time, it becomes a rotating magnetic field, and it has a magnitude, of course, n sub s times I sub s, number of turns of the stator winding. The rotation, omega s, is equal to 2 pi f, radian per second, and that's what we call synchronous speed. Now, that's what is created from the stator. Now let's look at the rotor winding. First, we're going to look at the lock rotor condition. When omega m is equal to 0, you have a rotating magnetic field from the stator, which rotates at the speed of omega s with respect to a stationary winding of the rotor. And what this does, it creates a current in the rotor, I sub r. But in reality, first it generates E sub r, the EMF, from F sub s, and that is d lambda dt. And lambda is the flux linkage, which means that if when the MMF is perpendicular to the coil, to the rotor winding coil, gives you maximum voltage. When it's horizontal and it's in same plane as a rotor winding, gives you zero voltage, because it's there's nothing penetrating through the area of the coil. And of course, the frequency of the rotor winding is same as the stator winding, because this is a condition like a generalized transformer. So in reality, we are talking about induction machines acting like a generalized transformer, especially when omega is then equal to 0. You're just like a transformer. Of course, the windings are not set up for the purpose of transformers. So now I'm going to go on and look at the rotor winding again as omega m. So we have I sub r rotating in the rotor winding. And what does happen when you have a coil and its number of turns, it has number of turns, and you create, what do you create? MMF by right hand rule. And so therefore you would create an F sub r generated by the rotor winding. And this MMF would rotate at a speed of omega r. Omega r is the speed of the rotor, the speed of the MMF with respect to the rotor winding. And in this case, since the rotor is stationary and the speed of the frequency of I sub r is same as frequency of the stator, therefore the speed of F sub r is equal to omega s. And what happens? We have two MMF, one at the speed of omega s from the stator and one at speed of omega r from the rotor, which is the same as omega s, since omega m is 0. This is a stationary winding. So when you rotate two magnetic fields, what happens? You generate torque. And now let's look at operation at any speed, omega m. So now the rotor is rotating at a speed of omega m. Initially was the speed 0, and it starts creating torque, and by that torque, rotor starts rotating, and it goes to any speed omega m. And let's see the process here. F sub r is n sub r times I sub r, and it has a speed of with respect to the rotor, omega rr, which is the speed of f sub r with respect to the rotor. And that would be omega s minus omega m, the difference between the speed of omega s and with the speed of omega r. Of course, if f sub s and and omega m are equal to each other, what are we doing? We are not generating any MMF in the rotor, and therefore omega rr would be 0. Now, the speed of omega r with respect to the stator is omega rr with respect to the rotor plus omega m. And if you substitute that here, you get omega s. So now what is happening? We get two rotating magnetic fields which are both operating and running at the speed of omega s. And what do you get? You get an induction machine producing torque based on MMF of the stator, MMF of the rotor, and the sine of angle in between them. And P sub m, of course, is the speed of omega m times your torque. So this is really the general concept from going from electrical to magnetic to mechanical energy. But in reality, what we're talking about, we see a machine physically, we apply the voltage, and we get torque on the shaft side of the machine. And we don't really talk about the internal process, which is the magnetic energy. This is the way all the machinery is, and the power system is really, it's all about operation of magnetic energy. Magnetic energy, without it, you would not have this rotation that we are discussing. Of course, you have other machines that can work from electrical to mechanical direction, but in induction machines and synchronous machines, the media in between is magnetic energy. The next topic is looking at the steady state operation of the machine. And the steady state operation is really looking at from the stator side, you have P and Q going into the motor. It generates a torque at omega m, T sub m. It's connected to a load that T sub L is the torque load. The load on the torque is proportional to to T sub m is proportional to I sub s, and T sub L, the load torque, is proportional to some polynomial of speed. Maybe it's just a first order, or second order. Most loads are either second order or omega m to the power of 2 or 3, or a combination of them. Under the steady state operation, Tm has to be equal to T sub L. So these are the general speed equations. The synchronous speed is 120 times F divided by number of poles. That is in RPM. In radian per second is 2 pi F. And that's the frequency of the system that is applied to the stator winding. S is your slip, and that is either in per unit or in percent, and it's omega s minus omega m divided by omega s. Essentially, is 1 minus per unit speed. So it's the reverse of per unit speed. Rated slip is when the machine is running, rotating at the rated speed, and that's called rated slip. Frequency of the system is F, and the frequency of the rotor at any operating point is called a slip frequency, and that is in hertz, and is S times F. So these are speed equations. The general equations that governs the machine, induction machine, it's just like a generalized transformer. You have the primary, which we call a stator, the secondary, which is called the rotor winding, and you got excitation branch and the core losses, R sub C, and then you have the rest of this portion right here is P sub M is the air gap power. So you have real power and reactive power that comes here, and it goes through here as mechanical power that goes to the shaft. And then, of course, what is delivered to the load is minus windage and rotational losses. We're going to see this a lot more later on as we go on. The general motor generator operation is very much has three operating points. One is the motor operation, which is from when the torque is at the starting torque, goes to maximum torque, and then comes down to zero at when the machine is running at omega s, synchronous speed. Everything comes to a halt when the motor or generator operate at synchronous speed, because the rotating flux of the stator and the speed of the rotor, which both are at omega s, they are in parallel to each other, and there is no flux linkage anymore. When you pass that point, you either have motor operation or generator operation. In the motor operation is in this portion right here, and the generator operation is after your omega m speed exceeds omega s. In the break area is when you actually get power back from the machine into the system. Next, we're going to see motor operation, where P and Q are the real and reactive power coming to the stator. And we see in this portion right here where you have mechanical power being delivered to the load. On the electrical side, apparent power can be in kilowatt or kVA or MVA, and it's real power and plus J reactive power. Power factor is real power divided by apparent power, and since P and Q are both operating flowing in the same direction, this would be a lagging operation. On the mechanical side, PM is T sub M times omega M, and that gives you kilowatt or megawatt. Efficiency now is PM over P, and it's always less than 100%. And acceleration torque is these two torques, mechanical motor torque and load torque, subtracted from each other. Under normal operation, this would be a zero value. If the acceleration torque is more or less than zero, then you have either acceleration or deceleration of the motor. On the generator operation, P is now P sub M is flowing toward the machine, and that's because omega M is larger than omega S. By some means from the load, which has a prime mover that makes it run faster than the speed of the synchronous speed of the motor. On the electrical side, P plus JQ is your power flowing, but they're flowing its opposite direction, and therefore is a leading power factor. Notice that Q in both operations is flowing toward the motor because the machine doesn't have an external DC field winding like a synchronous machine. The the field, the secondary or the rotor magnetic field is due to the induction of voltage from the stator to the rotor. So therefore Q always has to come to the motor, and therefore it becomes leading power factor. On the equation on that side is the same equation, except efficiency now is reverse, is electrical power divided by mechanical power. The next is rated values and motor equations that we want to discuss. On the shaft, you either have horsepower or kilowatt, rated kilowatt, and that depends on if you are buying equipment from US or Europe. Europeans are more IEC is rated kilowatt, and these are the shaft powers. And you got rated speed and rated torque. On the electrical side, you have rated voltage, rated kVA, rated current, and efficiency and power factor rated. But essentially, these are more or less efficiency and power factor at full load. The general equations: horsepower is 2 pi omega r T sub r divided by 33,000. Rated kVA, and the shaft again, is 0.7456 times horsepower. Electrical power is the mechanical power divided by efficiency. Rated kVA is kilowatt. Rated kilowatt times divided by efficiency and power factor. And full load amp is rated kVA divided by square root of 3 kV rated, because the kV rated is line-to-line voltage. And we refer to this as full load current or rated current. Required data for load flow studies are ratings, percent loading, and demand power factor. So in ETAP, we have 2 pages of information to deal with, and one is the info page and one is the nameplate page. And with that, I like to switch to ETAP. And bring up a medium voltage motor, which is in the first page. It has the conditions, that is service, out of service, and state of the motor, 3-phase or single-phase machine, number of quantity of motors, so you can actually have one motor that represents a group of machines same size. And then you have the configuration, where it states if your machine, if the motor is running continuously, intermittently, or is a spare. The next page are the rating on the top, which has horsepower, kilowatt rating, and the full load amp, and the kVA. Notice that you have, if I change the full load amp to 88 amp, the kVA changes. If I change the voltage, it would change the other one. If I change the horsepower, it would change the. All of these parameters are governed by the equations that we have discussed. Then you have power factor at full load, 75%, 50%, no load, and then you have overload, which you define what overload percentage is. Notice in here, down below, you have the percent loading. In ETAP, you have 10 loading categories, and you can specify the loading categories. And as you change these loading categories, for example, this one here at the winter loading, if it's like, I don't know, 30%, that would change automatically the motor load and the feeder losses for this motor automatically. So you can have different conditions of loading, and that would be showing the horsepower according to the percent loading. If I change the unit from horsepower to kilowatt, it's giving me a flag saying, do you want to use the same power factor efficiency? Because I'm really changing the size of the machine, and I say, okay, I'm using existing parameters. And now it becomes percent loading, and it shows you kilowatt according to this percent loading, and the motor load according to that. The we're going to come back and do more on these, but right now let's go and see how does a motor operates in ETAP. So when I go back to my PowerPoint, under steady state operation, we say a motor is running as a constant kVA load. And what makes that true is the fact, if you look at this table, I'm changing the terminal voltage of a machine from 90% to 110%. And this curve shows the terminal voltage from 90 to 100 to 110%. The trick for this guy right here is this part right here. As you change the voltage from 90% to 110%, the speed of the machine does not change much. And if the speed of the machine doesn't change much, on the mechanical side, the equations for the load torque is not going to change, so the load torque doesn't change. And if the load torque, which determines how much power is going to get from the system, doesn't change, so therefore the kilowatt from the system doesn't change. So the electrical kilowatt does not change much because the speed didn't change and mechanical power didn't change. Electrical power doesn't change much. The kilowatt, however, changes a lot because you got the voltage changes and you got the magnetizing branch, which sees the high voltage or low voltage. But notice the kVA doesn't change because the power factor of the machine is very high, 90%, 88%, 85%. So therefore kVA doesn't change much, and that becomes constant kVA load during the normal operation. And you can see based on constant kVA, if your voltage changes by 10%, the current goes 1 over 10%, which becomes 1 over 0.9. It changes by 11.1%, and vice versa. If it goes to 110%, the current comes down to lower value. So in general, when you run a machine at a very low current, if you run it at 90%, 95%, the current is increased almost by 5%, and the losses due to that current is going to go up by 25%, I square R. So as far as losses in the system is concerned, it's very much better to run it at close to 100% or a little bit higher, but not much more higher. We're going to see the limits later on and how much we should be running this machine. Now, the next item is how ETAP determines the power factor and efficiency as function of percent loading. So in the editor, I have I can put the percent loading at any value. So if it's 80% loaded, and that's this line right here, if it's 80% loaded, that means it's running somewhere right between the two items right here, or these two, power factor and efficiency. So if I go back to our PowerPoint, at any value, this is like around maybe 68% or whatever. We come up and we see then we calculate the efficiency, and here we go up at the same value and we calculate the power factor, and that's what ETAP does. So any value you see corresponding to that is based on these values here. This particular, these are typical curves that has been published for efficiency and power factor based on different size machine, 1 horsepower to 300 horsepower. But in the smaller machines, it doesn't make that much of a difference, but larger machines, you really want to get the manufacturer data. In here, I have one manufacturer data for 275 kilowatt at 6.6 kV. And this goes at loading 25%, 50, 75, 100, and 125. And those are these values, and the last one here is 125% loading. And you can see the curves as is expected. Induction machines are one of the most nonlinear element in the whole power system. It provides really a lot of nonlinear behavior, and you can see the power factor as function of loading, from zero loading to maximum loading or overload conditions. If you want to get the current, for example, and your power factor at zero loading, you can extend these curves, but you have to have these curves from the manufacturer, so it really gives you, especially for larger machines, you cannot just go on and put typical values for really large machines. Another example, this is another manufacturer, 2080 kilowatt machine, 5.5 kV, and again at the same conditions you can see the power factor actually going down, whereas in the other one the power factor was going, if I go up, the power factor becoming pretty much straight flat after it reaches 75% loading. So this is the way the machine behaves, and you have to get the manufacturer data. Next, we're going to look at the operating limits of the machine, where machine is represented as a back EMF behind an impedance with the terminal voltage V sub t. The back EMF is proportional to the frequency of the system and the flux in the machine. As far as the voltage limits are concerned, most motors are given as plus or minus 10%. And if I have a motor voltage, rated voltage of 460, then the terminal voltage has to be within 10% higher and 10% lower. So it becomes 414 to 506 volts. On the bus side, the bus voltage is 480. So if I go with the based on per unit or percent of the bus voltage has to be larger than 14% of 480. And or 5.4% of 480. So this tells you that when you have plus or minus 10%, but we're doing load flow analysis, you have to really be within the plus or minus 10% of the motor rating. So in ETAP, when we're doing the studies, if I run a load flow study, which if I look at this particular location, I'm going to go ahead and go to this portion of the system where I have two motors, and the terminal voltage, the bus voltage is 98%, and I can show the terminal voltage of bus as a function of bus voltage. So the voltage on the terminal of these two motors, though these two motors are identical with each other, and what I'm trying to do is to show you that 96.98% is based on the system voltage, which is bus voltage is 98% or is 480 volts. But I can change this to load terminal voltage, and so now it becomes 101%. So this is 101% of 460, where before was 480 volt. And this is your alarm level as far as the 5% or 5.4% in that in the equation that we just saw. Running under voltage, it increases your losses, and but it doesn't damage the system. But running over voltage on the motors is the best way to reduce the life of the motor. And if you go way above it, then you're really going to damage the motor very fast. So that's one of the things to be really being aware of, the over voltage and under voltage, of course. Going back to the rest of the limits, the other one is the frequency limit, and a lot of machines have the frequency limit of plus or minus 5%. But the plus or minus 5% is really based on transient frequency, not operating at plus or minus 5% on continuous conditions. Notice again, if you increase the uh, frequency by any value, and if the terminal voltage is fixed and the back EMF is fixed, by increasing the frequency, the flux is going to go down, or by decreasing the frequency, the flux goes up, and that introduces extra heating in the machine stator and rotor windings, and that's you pass in the limit of the heat limit without really having an overload condition. It's just by changing the frequency. So if you buy a 100 horsepower machine from US and go to Europe and connect it to a 50 hertz system, and you use the same voltage, as rated voltage, as the frequency goes down, the flux goes up, so therefore the mechanical power has to be reduced by 5/8. But even if you do this, your heating in the rotor is still increased, and it reduces the lifetime, even if you run it at the lower power. It's not a good idea to do such a thing. Next, we're going to consider motor feeder cable. ETAP provides adding the motor feeder cable directly in the editor as part of the motor, where you specify the size and the information about the cable, and you can see the loading of this machine, percent loading, and the voltage drops, and the terminal bus, and the voltage at the load terminal bus. And I'm going to discuss the difference between the two methods of doing this. So if I go back to ETAP, now I'm going to be looking at the ETAP one-line diagram again. And in this case, what I like to do is to zoom in this portion of the system right here, and show you the process of adding a cable internally to a motor. These two motors are identical to each other, so I'm going to go do a Control C, Control V, and then move this motor here. Oops, I moved the wrong one. And connect it to this bus. And once I have it connected, I'm going to go ahead and I can add a cable to this and insert a cable, but I don't want to do that. What I want to do is to go right here inside the motor and go to the page cable here, cable and voltage drop, where I can go ahead and add a cable. I take something, I don't know what cable I need to select, but this is a 60 hertz machine, so I would go to 60 hertz 3-conductor cable, copper, and select size 8. Let's just select size 8. And I'm going to go ahead and put the same concept here, 500 feet of cable. And you can see right away that if I at 100% voltage, the terminal bus of this machine is going to be 83%. So that tells me right away I picked the wrong size cable. So if I go up to 1 aught, it goes up to 99.6%. But I like to go to the ampacity page, and let's say I'm going to be putting this in an underground duct bank, 3 rows, 5 columns, and you can see that the full load amp of the machine is 108, but my derated ampacity is 81.6. So this tells me that the current I have a problem with the current of this cable. So 1 aught produces up to 2.6% voltage drop. So I'm going to go ahead and go to a 4 aught, and now I can see the voltages are dropped. Voltage drops are dropped. But if I go to the ampacity, now I have 120 amp derated ampacity and 108 amps, which is full load amp of the machine. If I go to the operating, I don't have operating. I have not run a load flow in this machine. But if I have a multiplying factor of like 25% for the first size cable, I do not match that, but I don't care for that. This one right here, and so I'm okay with this now. So now I can go ahead and run load flow again, and you can see this guy here is doing the same thing as this particular one is doing, and the difference here is the fact that I have added a new bus because I have external impedance or cable. So therefore, although I get the same result, but when I do external one, I have to get back and forth to see what size of the cable I need and so on. Whereas here, I'm seeing it in the same editor, and I save a bus. So if I have 1,000 motors in the system, I need another 1,000 nodes in the system for operating the system, the nodes, the motors in the system. So with this, I think it's obvious that having internal cable, which you can still come to the cable editor by double clicking on it. So this concludes the operation of the machine for steady state operation of the machine, fundamentals, and the next series would be on the machine more acceleration. Thank you very much for paying attention, and we will answer any questions at this point.